my classes on fundamentals of electrical engineering. After completing the first module, wherein we talked about electrical circuits, one of the application area was DC was machines. So we went on to electrical machines, and so we completed DC machines. Okay, in two sections. Now we are on transformers. Can we have two sections there? And now we move on to another class of transformers which are of prime importance and which happen to be everywhere. That is the three-phase transformers. Okay, so three-phase transformers, though I have always maintained that an extension is possible whenever we look when we from single-phase transformers. There are a few things, like for instance the connections matter, especially the star delta connections matter, and that's the reason why you have most of the problems oriented along this direction. Okay, let's hope that we'll be able to be comfortable with three-phase transformers also, especially with respect to the connections. Okay, so I'll try to help you. Okay, the first problem is a little different. Okay, it has just been, it's not a problem, it's just a statement. It tells us that in a constant voltage transformer where we use capacitors, no doubt about it, but the output is maintained constant using the tap windings. Okay, just by changing the that's why it's called as a constant voltage transformer. Okay, so though capacitors are used, the constancy is maintained using tap windings. Okay, that's all. That's just a statement. Okay, let's move to the next one. Okay, here we start with the connections. Then three-phase connections can be used in a transformer to introduce a phase. Which three-phase connection can be used in a transformer to introduce a phase difference of 30 degrees between its output and corresponding input line voltages? This is a very important understanding that we need to have, and that decides the configuration of the transformer. So transformers are explained as YD1, YD11, DY11, etc. So which will be coming to. That's a kind of specification, and here we must realize that to get the 30 degrees phase difference, you always need to have what is called as a star on one side and a delta on the other side. Okay, it could be reversed, but in this case star and delta is given as the second option. All the others are either star star or delta delta or delta zigzag. Okay, zigzag is a different context altogether, but a star delta will always give you a 30 degrees phase difference. A small diagram has been drawn there, wherein the linkage between the star and delta, that is phase windings, are shown along the same axis, because that's why they are linked together. Okay, so if we have VAN, that is VAN on the primary side with the capital A, then VAB on the delta side, if it's there, will be along the same axis. Okay, when you are representing in terms of vector diagram. Okay, so when you are taking the line to line voltage of both, that it is seen that one of the phases in the phase winding or in the star winding has to be taken to the has to be reflected back, and then the resultant needs to be found out, and so they automatically the 30 or obviously 30 degrees creep into the line voltage versus phase voltage between the star and delta. Okay, so that's what is shown there. Okay, so yeah, that's also an indicator alone. So we move to the next one. That is the third problem. Okay, this is a numerical one. A three-phase transformer has ratings of 20 MVA, 220 kV star, okay, and 33 kV delta. So what do we have there? Each of these phases link. So 220 by root 3, that will give you the phase voltage that is going to link with each of the phase winding of the delta. Okay, that kind of visualization is important for three-phase transformers. Okay, with leakage reactance of 12%. The transformer reactance in ohms referred to each phase of the LV delta connected side. Delta connected side is good because the voltage that is given happens to be the phase voltage as well. Okay, so the phase voltage happens to be 33 kV. Okay, and the transformer rating is 220 MVA, and the leakage reactance is given as 12%. This can be on any of the sides. Okay, and what is required is the transformer reactance, not the percentage value, but the reactance, and that too on the low voltage side, which is good for us because we can easily find out the base impedance on the low voltage side. What's the base impedance? 20 by root 3 has to be taken because that gives you the per phase MVA, and the per phase voltage is 33 kV. So kV square by MVA, or 33 square divided by 20 by 3 will give you a base impedance of 163.35 ohms. Okay, that's all that's required, because base impedance multiplied by the percentage impedance expressed in per unit will give you the real value of the reactance, and that's what is done here as equal to 19.6. And from the options we select B because of that. Okay, because that's obviously true. Okay. Fourth problem, a three phase, three winding, delta delta. Okay, so we have three winding and we have delta delta star. Okay, so we are having three sets of windings. Okay, not exactly a zigzag winding, but delta delta delta. Okay, and the three voltages are also given as 1.1 kV, 6.6 kV, 400 volt transformer is energized from AC main set. So 1.1 voltage is the energizing side, and then you take out the voltages for 6.6 kV and 400 volt. Okay, such transformers are there in many situations, real situations. Okay, and because the same transformer, the same core can be used for different purposes. Okay, it supplies 900 kVA load at 0.8 power factor lag. Okay, so you can have both the active power and reactive power just because 0.8 is given. Okay, but let's continue with the problem. 900 kVA is what is required, and that's it, 0.8 kVA from the 6.6 kV winding. So that's the load side, and 300 kVA load at 0.6 power factor lag from the, so both are lag. Okay, and that's from the 400 volt side. So both windings are loaded, that is both the secondaries are loaded. Okay, the RMS line current in amperes drawn from the 1.1 kV from the mains. Okay, so here please remember that you can do it in a very simple manner. Only voltages, only current is asked. So VA is all that is required. You already have the voltage, and we have VA. So we just need to find out what is going to be the current. Okay, so this has to strike you first. Okay, this is what we call as clicking for the answer. Okay, so what do we have here? Please realize that whatever be the kilowatt demand, whatever be the war demand, 900 and 400, 900 and 300 kVA, that is 1200 kVA has to be given by the transformer. Okay, it can be whatever be the type of winding. Okay, it doesn't matter, because there is no winding, there is no turns ratio etc. for kVA or MVA or whatever, and kilowatt and watt, var etc. So 900 can be added directly to 300 kVA. So together they make the transformer has to deliver 1200 kVA at what voltage? 1.1 voltage. Okay, and that is going to be a line to line. That's going to be okay. Whatever the equation is root 3 IL VL is equal to kVA. So we are having root 3 1.1 because kilo, and then IL is the only quantity that's not required, that's not available. And why do you have that root 3? Because per phase quantity is going to come in a delta. So to get the line current, you have to multiply by root 3. That's the reason why root 3 is appeared here. So root 3, and the equation can also be used blindly, which tells us that the total kVA will be given by root 3 VL IL. Okay, where both are line quantities. So line voltage is already the same as phase voltage, which is 1.1, and we are using kVA, so you can use kV, and then amperes IL is what is going to emerge, and that's the same as equal to 629.84. But just by substitution, 1200 is equal to root 3 into 1.1 into IL. So IL is equal to 1200 divided by root 3 and 1.1. Very simple. Okay. Yeah, so now we can easily do the fifth one as well. If the primary line voltage rating is 3.3 kV on the delta Y side, so immediately 3.3 by root 3 will be the phase voltage should be coming in your mind. You need not calculate anything, because most of the problems you can just simply strike off some of the quantities and you can arrive at the answer easily. Okay, the last minute kind of calculator usage is the best method. Okay, so primary voltage is 3.3 and the kVA rating is 25 kVA, and the style is, or the configuration is star delta. Okay, transformer as per phase turns ratio is 5:1. Okay, so turns ratio is 5:1. That is V1 by V2 is equal to 5, or I2 by I1 is equal to which is the same as equal to 5. Okay, V1 by V2 is equal to I2 by I1 is equal to 5. Okay, then the line current rating, that's what is asked. The line current rating of the secondary side is what? Okay, so what is the secondary side? It's a delta. Okay, so root 3 times is required for the delta, because you can get the phase quantities, okay, based on phase voltage ratios, and then you can multiply by root 3. I suppose that's clear. Okay, so that's the first. So 3 things should be in your mind immediately. One is, of course, what is the configuration. So we have star on one side. So if you are given 3.3 kV, the phase voltage is going to be 3.3 by root 3. Okay, that's one thing. Second is there is a delta on the other side. So 3.3 by root 3 is going to link with each of these phase phases. So whatever voltage we have will be phase voltages there. Okay, but then currents also will be accordingly obtained. Okay, if you use the transformation ratio, but then you have to multiply by root 3. Why? Because so that's the third thing, because you have asked for line current. Okay, so once all that is clear, we can easily do the line current in the primary. What is the line current in the primary? Because we are having 25. Okay, 25 divided by root 3 and VL. Okay, root 3 and VL is sufficient. Or else you can go for the phase by 3 into, okay, things like that. Okay, 3 into root 3 by 3.3 by root 3. Okay, so or other than that, 25 divided by root 3 VL. Okay, so we have 25 divided by root 3 into 3.3 gives us a particular quantity which has not been computed now, because it can always be used at the last moment. Okay, now what do we have? Now we use the, now we go to the secondary side. Okay, so now we have the line current, which is the same as the phase current for the star side. Okay, so phase current can be immediately brought to the secondary side using the turns ratio. So what do we do? 25 divided by root 3 into 3.3 multiplied by 5, because because we are finding out I2 now. Okay, not I1. Okay, from I1 we move to I2, so multiply by 5 rather than division by 5, which is applicable to voltage. So multiply by 5. Okay, and then remember the root 3 that we talked about, from the phase currents we have to go for the line current. Okay, so I repeat, what we have here is 25 kVA divided by 25 kVA is now going to draw a line current which is the same as the phase current for the delta side, for the star side. Okay, then you can immediately multiply it by 5 to get the star side current. Okay, so 25 divided by root 3 and VL will give you the phase current and the line current, which are the same for the star side. Multiplication by 5 will give you the delta side phase current, and another multiplication by root 3 will give you the line current. Okay, so one after another, if you set them together very easily, you can see that the answer is going to be 37.8. There's absolutely no requirement for any, there's absolutely no need for any kind of doubts in this area. So if you can picturize it all in your mind. Yeah, so let's go to the sixth problem. Three single phase transformers are connected to form a delta star. So primary is delta, and the other is a star, that is the secondary star. Three phase transformer of 110 kV by 11 kV. So on the delta we are having a phase voltage of 110, and on the star side we are having a phase voltage of 11 by root 3. Okay, so if you are asking for the if in any manner the transformation ratio is required, you go from face to face. Don't never go for line to line quantities. Why? Because here we are having a problem in the sense that linking happens between phases. Okay, so 110 divided by 11 by root 3 is going to give you the turns ratio if it is required. Okay, the transformer supplies 11 kV. Supplies at 11 kV a load of 8 megawatt at 0.8 power factor lagging to a nearby plant. Okay, so this is what it is doing. It's supplying a line voltage to a plant, and it's giving 8 megawatt at 0.8 power factor. Okay, neglect the transformer losses. The ratio of phase currents in delta side to star side. So much of material has been given, but what you require is only the transformation ratio, because transformation ratio, the voltage side, as I said, is very clear. It's equal to 110 divided by 11 by root 3. Okay, and then you just simply if that is going to be K, 1 by K is going to be the current ratio, and current ratio is given as 1:2, so that's equal to 10 by, let's say 110 divided by 11 is 10 into root 3. So 10, because root 3 has come on the numerator, so 10 into root 3. So if you look at the current, it's going to be 1:1 by 10 by root 3. That's what 10 into root 3. Okay, so answer is correct. Okay, very simple. You don't need anything. Okay, so this is a little different. Okay, because we are having two transformers shown with dotted terminals, and the primary is marked with capital letters. Okay, this is the normal trend. Okay, primary is marked with capital letters, and the secondary will be marked with small letters. Okay, these are nomenclatures or notations which express what is there inside a big box, which happens to be a transformer as far as a layman is concerned. Okay, and then the dotted terminals are also important because it tells us about the mutual induced EMF, etc. Okay, so let's read the problem. The star side of the star delta transformer, obviously it's a star delta transformer shown in the figure, is excited by negative sequence voltage. So we have having a small change. What happens if a negative sequence voltage is given? Then we are going to have a change in the sense that if the star side voltages are shown on the right hand side, that is on the right hand side, and left hand side the delta is immediately picked up and given there. So we see that because of the linking between phases VAN, okay, VAN and VAB. Okay, so you can see VAB is inclined by 60 degrees, just like VAN. So they link with respect to each other. Okay, so then let's see what is horizontal. Horizontal happens to be yeah, if we have called it, we have called the first winding as AB, then BC happens to be just start with the dotted terminal. So the winding BC is now linking with BN because they are both horizontally placed. So physically they will be linking with respect to each other. Okay, and then from the dotted to the other, the last of the winding CA is now linking with CN. Okay, because they are oriented at a 120 degrees also, just something like that. Okay, to tell us that physically this is the situation. Okay, so now so we see that VAN. Okay, so now we come to the negative sequence excitation. Okay, so when you look at the right hand figure, the negative sequence excitation tells us that is if we of course need to go in a clockwise manner. So the next voltage, okay, if VAN is set here, it won't be VBN unlike in the earlier cases, because it's negative sequence voltage, we'll have ECN and then we'll have VBN. That's the only difference that's there. Okay, and now but VAN links with VAB. VAB is talking about the winding that we saw earlier, and VCN is linking with VCA, and VBN is linking with VBC. That is between the primary and secondary. And what is asked is, yeah, so what happens? VAB leads VAB, that is the primary. AB leads the secondary AB by 60 degrees, or said VAB lagging VAB by 60 degrees. The first mention is always going to be the primary, or VAB leads. Okay, so all four options. Okay, so now for that we just need to have a picture in our mind. So I've just drawn here. So what do we require? Okay, so we want to have VAB. We only have VAN, VBN, and CN on the primary side. So we have to get VAB. How do you get VAB? Project B backward, because we need, if you want to have VAB, B needs to be projected because B is mentioned second. Okay? So we project it backward and then we get the resultant as VAB. Okay? So it's obvious that VAB on the primary side and VAB on the secondary side, how are they related? You just go in a clockwise manner, and then what do you encounter first? You encounter the delta side first. Okay, so in that case, that leads, that is V small AB leads V small capital AB. Okay, so what is that? So where do we have? V capital AB lags. Okay, what comes next? Lags. So capital V. Okay, so you go in the clockwise manner, and in the same sector, in the same quadrant, you have to see both. Okay, so you see that small V small AB is a leader, or V capital AB is going to be the lagger. Okay, so that's option D, where VAB capital AB or the primary lags the secondary. Both ABs are the same, or they are both now can be called as line voltages. Though in the delta it's phase voltage, but phase voltage and delta voltage are same. So the line voltage, when you compare, you see that VAB lags VAB by 30 degrees. Okay, or primary lags the secondary by 30 degrees. Okay, yeah. So we now have another problem. Yeah, what is that? We have three winding. Okay, let's look at the problem first. We are having one single big turns. Okay, which is now giving power to two windings. Okay, and the first winding is energized, and we are having second and third windings. One is carrying a current I1, and the dotted terminals are shown. And we also have N1 is to N2 is to N3, and I1 and I2 and I3. Okay, and they are all loaded. Okay, what do we have here? The three winding transformer is connected to an AC voltage source as shown in the figure. The number of turns are as follows. Okay, N1 is equal to 100, N2 is equal to 50, and N3 is equal to 50. Okay, so they are so in total. So 1 is to, yeah, the voltage, if you have, it's going to be 1. Okay, it's 100 by 50 or 2. Okay, and the current will be half in the secondary windings, but the voltages will be, okay, the primary will have a higher voltage and a lower current. Okay, but the current in the secondaries, two secondaries will have double the current. Okay, so that's it. Okay, the magnetizing current is neglected, and the currents in two windings are I2 is equal to 2 angle 30 degrees and I3 is equal to 2 angle 150 degrees. Okay, so there are two currents. Okay, and then what is the value of current I1 in amperes? Okay, so what do we have here? We are having larger currents in primary and secondary, because the winding turns ratio is 2. Okay, so it's going to be half, or in other words, you have to you have to, yeah, so that's how you're going to do. So 2 angle 30 and 2 angle 50, 150 need to be added together. Okay, but then of course when they are coming to the primary, because the current is going to reduce there, okay, divide by 2 in both cases. So 1 angle 30 is to be added to 1 angle 50. Okay, so you can see that 1 angle 30 and 150, 1 angle 50 are okay, they with the vertical they make each of them make 60 degrees. Okay, so it's going to be at the vertical, and it's going to have a value as equal to 1 angle 90. Okay, so yeah, so that's the situation here. I hope it's clear. Okay, so the ninth problem, so the ninth problem again, looks a little confusing, but you'll have to follow the winding. How do you follow the winding? You first look at the primary only. Don't ever avoid the secondary. Just look at the primary. What do you see? There are three phases. Okay, there are three phases which are now delivered to both the windings. Okay, the first one at the top and the second one at the bottom look to be the same, because the A is delivered to A2 in both cases. Phase B is delivered to both B2 and both the B2s, and for phase C2 is delivered to both the C2s. Okay, so delivery is okay. Now what do you see? The phase comes to A2, or current comes to A2, and then it flows to A1, and then it goes to B1. Of course, we have already talked about the connection coming to B. Okay? Then it goes to B1, then it gets connected, and then it goes to the third winding, and then it arrives at C1, and then it goes back. So what do we have here? We have a delta. Okay, the same thing is true for the winding at below it. Okay, we see that the current arrives at A2, it moves through the coil, arrives at A1, moves through the goes to coil B. Okay, arrives at B2, goes to B1. Okay, arrives at C2, goes to C1, and then goes back. Okay, so this is the absolute structure, or the exact structure of a delta. Okay. The primary side is resolved. Okay, and then we are having windings on the other side, which are linking with each of them based on the geometric kind of show that is on the slide. Okay, so what do we have there? We again have, let's look at the primary. We have let's look at the secondary, the first quantity, and we are shown a V1 voltage also there. We see that A1, A2, yeah, so if of course the output is connected to A2. Okay, and then if there's a current flow inside, then it flows to A1, then it goes to B2, and then it flows to B1, and then it's go to C2, C1, and then back. Okay, so again delta is there. Okay, and then we are having, okay, the next, the one below is very clear. It's a star winding, because we are having A1, B1, and C1 as common points, and the output being taken from A2, B2, and C2 respectively. Okay, and now what's the question? Two three-phase transformers are realized using single-phase transformers as shown in the figure. Okay, so we are having so many single-phase transformers put together. Okay, such that we are having such a structure. Okay, delta on the primary side, star and delta on the secondary side. Okay, so what is asked is the phase difference between voltages V1 and V2. Okay, so the diagram will explain many things much more than what is asked. So that's the reason why I put it there. Okay, so let's look at only the secondary. Why? Because the ratio of the angle between V1 and V2 is asked. Okay, so what do we have there? Let's picturize A2, A1. Okay, why do we call it as A2, A1? Because because we started at A2. Okay, so if you are calling it as A2, then the pointer is marked at A2. Okay, so let's use the same pattern. If this is called as A2, A1, then the next one is B2, B1, and then it's going to be C2, C1. And the same, okay, that is of course clockwise span. Okay, that is the electrical angle progression. Okay, so we are having A2, A1, B2, B1, and C2, B1. Why do we draw it in this manner? Because now we need to find out which is V1. Okay, that's the reason why V1 is pointed with an angle is written with the pointer where the point is on A2. That's the reason why it's called as A2, A1. Okay, so what is V1? V1 is just the voltage across A2 and A1, isn't it? This is the voltage across A2 and A1, because B2 and A1 are common. B2 and A1 are connected together. So that's V1, and that's the reason why now A2, A1 describes V1. Okay, now let's describe V2. What is V2? V2, because they are both linking in the same manner, the two transformers. Okay, so we can set them again in the same space. Okay, so what is V2? V2 is going to be, okay, it is pointing at A2, okay, and it is starting at B2, so it's going to be B2, A2. Okay, but where A1 and B1 are connected together. Okay, so we already have A2, A1 just as before. Okay, and we also have B2, B1. Okay, and now we reverse B2, B1 such that it becomes B1, B2. So if we add A to A1 to B1, B2, because A1 and B1 are the same, you get what is called as A2, B2. Okay, this is what is called as B2. Okay, that's what you call as B2. Why? Because B2's point, the pointer, pointer of the phase voltage V2 is pointing at A2. Okay, so just the same convention has been followed. Okay, and that's the reason why we can easily compare V2 and V1 as having an angle difference of 30 degrees. Okay, I hope this diagram is completely understood. Once you have this, okay, then three phase becomes so easy. Okay, you just move through it in a very easy manner. Okay, I suppose this is clear. The convention is what is very, very important. Okay, so if you are calling it as A2, A1, it means that the pointer, okay, that is A2 is at a higher potential with respect to A1. That's the meaning. Okay, so and we are just assuming in one particular manner. If you assume a particular situation, then it continues for all the phases. That's all that's there. I hope it's very clear why we write A2, A1, B2, B1, and C2, B1. Okay, and then if because we want to find out what is V1, and V1 we call it as equal to the voltage across A2 and A1. So we already have it. Now we want to find out V2. Okay, so where does it point? It points at A2. And what's the starting point? It's going to be B2. So we already have B2, B1, but we can't add A2, A1 and B2, B1, but we can add A2, A1 and B1, B2. That's because A1 and B1 happen to be the same point. Okay, so you add this, so you reflect it back, and then you add it. Okay, and you find the resultant. That's going to be V2, and you call V2 as equal to A2, B2 because it starts at B2 and ends at A2. Okay, so where that is the pointer. Okay, so the pointer is an indicator. That's all. Yeah, so we go to the last slide and the last problem. What do we have there? A balanced star connected. Okay, so what do we have here? Let's see. We see a star connected. Yeah, we see a star connected load 4 ohms. It is connected to a delta winding. Okay, and on the other side we are having a star, and then the entire configuration is now moved to a star configuration. This is what it looks like. Let's see. And all of the resistors are having a value of equal to 4 ohms, and the voltage, the turns ratio or the voltage ratio happens to be 110 by 220. Okay, or 1:2. Okay. So, yes, let's start. A balanced star connected purely resist load is connected to the secondary of a star delta transformer as shown. Okay, so we have that. Okay, the line to line voltage rating of the transformer is 110 by 220. Okay, so 110 by root 3 by 220 is a better way of expressing. Why? Because the primary happens to be star connected, so its phase voltage is 110 by root 3, which now can be compared to 220 volts, because 220 volts, though it's a line voltage, it's also the phase voltage on the delta side. Okay, just as we have been talking so many times. Okay, neglecting the non-idealities of the transformer, the impedance Z of the equivalent star connected load referred to the primary. So everything has come to the primary. Okay, it has traversed the entire domain of the delta, then the linkage between them, and has arrived at the primary. Okay, so how does it arrive? Using a k-square quantity. Okay, so before that we have to see how we can match everything. Okay, let's bring them all to the phase situation. So if you want to have a phase situation, because all resistors are going to be 4 ohms, you can immediately build a delta out of it. How do you get a delta? Because they are all equal, you just multiply by 3. Okay, so each of these 4 ohms becomes, in a delta they become 12 ohms. Okay? And now this 12 ohms now needs to be taken to the primary side. How do you take it? By using k square. What is k? 110 by root 3 by root 3, because you get to have a voltage ratio between the two phase quantities. So 110 by root 3 divided by 220. Okay? So that's equal to 1 by 2 root 3. Multiply, square it. So we are having 1 by 2 root 3, or 1 by 4, 1 by 12 multiplied by 12, which is giving us an answer equal to 12 by 12, which is equal to 1. It's a good answer, and immediately you should be confident that you have arrived at the correct answer. Moreover, there aren't any inductive quantities at all. So any of all the j values you can reject. Okay, and so the option is between A and D. And of course, now we have seen that because of the voltage turns ratio, giving rise to a k-square quantity for the secondary quantities to migrate into the primary domain, we have what is called as, we have a reduction in the impedance, and so we have 1 ohms. Okay, so that's all that's there. I hope the star delta connection is very clear to you. Okay, and the phase quantities. Okay, this is what we have been focusing more and, okay, or emphasizing further and more. That is that the construct of the, or the configuration of the star delta or the transformer is very, very important. Okay, what is phase value? And whenever you are taking turns ratio, remember to use the phase quantities. Okay, and then also remember that V1 by V2 is the same as equal to I2 by I1. Okay, so that's important. And then we also see that we have to have a that if we call V1 by V2 as K, then K square times the secondary quantities migrate into the primary domain or primary area. Okay. So I suppose we have touched on most of the important things. Okay, so when I consolidate, I may not be able to do the drawing, etc. So please have a good look at, or have a good understanding as to how the phases and the line voltages, etc., behave with respect to three phase quantity when they are in the star configuration and also in the delta configuration. And the most important aspect happens to be that how physically are the two windings located determine the linkage between them. Okay, and they will be along the same axis as far as the vector diagrams are concerned. Okay, so thank you.